Hello and welcome back. In section 2.1, we do a quick little review of functions. So, we can't talk about functions without starting with a relation. So a relation is some correspondence, some relationship between two sets. We can identify those either by a mapping diagram or ordered pairs. So set number 1, we have A, B, and C. Set number 2, we have 1, 2, and 0. And here the arrows indicate how the elements of set 1 are related to the elements of set 2. Equivalent ordered pairs would be A, comma 1, B, comma 2, and C, comma 0. So we're going to let cap x, cap y represent two non-empty sets. Function from cap x into cap y is a relation. So all functions are relations. Functions are just one special subcategory of relations. So every function is a relation. Not every relation is also a function. So a function that does what? Associates each element of x with exactly one element of y. The exactly is more there for emphasis than really needing to be there for the definition. Generally speaking, if you're telling a number and not saying at least or at most, it's assumed you mean exactly. So our previous example is both a relation and a function. It's a relation because we have two collections that are related somehow. It is a function because every element of the first set goes to exactly one element of the second set. Let's get another quick example. So we'll map A to 1, B to 2, C to 0, and we'll map D to 1. This one also both a relation and a function. So it doesn't necessarily have to have the same number of elements to still be a function. Let's see if we flip this around. Let's say we'll map C to P, D to Q, E to R, and F will match to both S and T. So U has been untouched, that's okay. But here we have one element from what we're generally thinking of as X are input values, having two output values. This one is not a function. It is still a relation, however. We have things from one set mapped to things from another set and some type of description on how they're related. So hopefully that first little bit was mostly review. Of course, we're more used to seeing equations in math class representing relations and functions. So for example, y is 7x minus 19. No matter what real number I plug in for x, if I multiply it by 7, I only get one answer. Take 19 off of that one answer, I get one value when I'm done simplifying. Every x value corresponds to exactly one y value. So this is both a relation and a function. But if we look at x squared plus y squared equals 15, you should hopefully remember from section 1.5 what that looks like. This one is a relation. But not a function. To show me that it's not a function, you just have to show me one counterexample. So show me one x value that gives you two y values. So I'm just going to let x equal 1. So 1 squared plus y squared equals 15. So y squared is 14. So 1 squared is 1. Subtract 1 off both sides. Square root of y squared is plus or minus square root of 14. Y is plus or minus root 14. So there was one input value, two output values, therefore not a function. So you just have to show me that. There could be a million examples. You only have to show me one of them to show that it is not a function. So if it says prove that it's not a function, this is how you prove it. Pick an x, show that it has two y's, or whatever your input and output variables are. A little review on function notation. Again, hopefully most of this is familiar. We'll look at f of x is 3x squared plus 7. So just like in your Math 95 days and 100 days, they would ask you for things like f of -4. That just means replace all of your x's with -4s, bring everything else along and simplify. So f of -4, 3 by positive 16 plus 7, so 48 plus 7. So f of -4 is worth 55. That's equivalent to also saying we have the ordered pair -4 comma 55 on our graph. It's not always necessarily constants that we're plugging in. We might ask to be looking at f of, say, 2x. Same idea though. Now it's saying replace all of your old inputs in this framework of f. So 3 times something squared plus 7, but your something now is a 2x. And just simplify from there. So we have 3 by 4x squared plus 7. So we have 12x squared plus 7, and that's as far as we can go on that one. Let me bring that along. Now we'll start a new one. We'll do g of x is x squared minus 5x plus 2. So they might ask us to find f of, say, x plus h. G of, my apologies, g of the quantity x plus h. Same idea. This says follow the framework of function g, something squared minus 5 times something plus 2, and plug in whatever the something was that they asked us about, in this case, x plus h. This is a really good time for a reminder. A plus b quantity squared does not equal a squared plus b squared. If you want to convince yourself of that, try out doing 2 squared plus 3 squared and 2 plus 3 quantity squared. You'll see you have two different values for that. Don't forget to FOIL out if you are squaring a binomial. So x plus h by another x plus h. You can distribute the minus 5. So x by x, first by first, is x squared. Outside gives us hx, and inside also gives us hx. So we have two of those hx's, and last in each, h times h is h squared. And here I don't see any simplifying that I can do. That's as far as we would go on that one. They might ask us to do things with that. They might ask us to also find g of x plus h minus g of x all over h. In this case, it's another question of substitution. I already know what this piece looks like. I know what this piece looks like, and I'm just subbing an h in at the bottom. So g of x plus h, that's our x squared plus 2hx plus h squared, minus 5x minus 5h plus 2. From that, we're subtracting the original g of x. That's more than one term, so make sure you're using grouping symbols, brackets, parentheses, whichever one you picked out. H is downstairs. We do have some canceling happening, though. So just like any of the other ones before, simplify where you can. X squared minus x squared is 0. Negative 5x minus a negative 5x is 0. 2 minus 2 is 0. You might also notice that of the terms we have left in that numerator, they all have h involved. So let's go ahead and factor that. So we hang on to both sides of our equation. We don't lose one side or the other. So h is multiplied by 2x plus h minus 5. So I factored an h from all three of those guys and an h downstairs. H divided by h is a 1. So this is worth 2x plus h minus 5. That's as far as we can simplify on that one. Something you're going to see more of as you move forward in your math career: implicit form versus explicit form. We'll start with just a linear. X plus 2y plus 7 is negative 14 is an implicit form of an equation. We don't have one variable by itself. Explicit form has a variable by itself. So, for example, y is negative 19/23 of x plus 42. This would be an example of a linear equation that is in explicit form. So they may ask us to switch between them. So they may ask us to find the explicit form of 3x squared minus 2y is 8. Basically, on that one, we want our output variable by itself, so I'll subtract 3x squared on both sides. So negative 2y is negative 3x squared plus 8. And then we'll just divide both sides by negative 2. So y is positive 3/2 of x squared minus 4. So don't forget, both of these were divided by the common denominator of negative 2. If you find yourself making that mistake a lot of just leaving the 3x squared alone and only simplifying this part, just think back way back to your arithmetic days. The same thing that allows you to add, say, 1/7 and 3/7 and get to 4/7 is that you added the 1 and 3 together and kept the common denominator. And remember, in math, if you can start here and go this way, you can also work backwards as well. So if you need to write out the step explicitly in here, saying, okay, -2y over -2 is then -3x squared over -2 plus 8 divided by -2, and simplify from there. If you need that one extra step, take that one extra step. All right, so another common topic in functions, the idea of domain. When you're thinking domain, just think of what would make me break a rule. What would kick me out of the real numbers? So if my function is just 5x squared minus 2x plus 19, there's nothing in here that I can plug in for x that would make me break a rule. So here, my domain, you'll either see it written in interval notation or set builder notation. So this one, now that I have a fraction involved, there is one value of x that would make me break the division by 0 rule. Remember, division by 0 is considered to be undefined. So -2 plugged in for x, I would have some number over 0. Anything over 0. So it doesn't matter what number that is. Happens to be 7 this time, doesn't matter what it was. If it's over 0, it's undefined. So my interval notation for this guy, -infinity up to but not including -2, union that up with -2 through infinity. Or if you want the set builder instead, set of all x such that x is in the set of real numbers and x is not equal to -2. Another common place to watch out for breaking common rules: square roots, fourth roots, sixth roots, any even roots. So here, to avoid getting kicked out of the real numbers, remember, anytime we have the square root of a negative, that kicks us into complex I territory. So we want we'll use a let line, let the inside be at least 0. So x is at least -3. So interval notation, -3 through infinity. We can never get to infinity, so that's going to get a parenthesis. Or if you want it in set builder instead, set of all x such that x is in the set of reals and x is at least -3. And the last thing we review in section 2.1 is operations on functions. F plus g quantity of x just says, okay, take f of x and add g of x. The minus works the same way. Use a small dot if you're doing multiplication. Composition, of course, you don't want to get that confused with composition. Multiplication and composition, very different operations. So small little dot for the multiplication here, I did not mean to make that one even bigger. And of course, division, f over g of x. It's just f of x divided by g of x. We do have one restriction on the domain, so g of x cannot be the zero polynomial. So since part of those are review, I'm going to give you an f of x and a g of x and have you see if you can find each one of these and state the domain. So state the domain for each. So we'll do f of x. That'll be x squared over x plus 4. And g of x will be x over x minus 3. So pause it for a minute, try those out, and then unpause it, and we'll run through these together of finding each one of these four. Okay, welcome back. So I'll start with f plus g of x. So that is x squared over x plus 4 plus x over x minus 3. So LCD is just the product of x plus 4 and x minus 3. So just build up your common denominator. So f plus g of x, x cubed minus 3x squared, plus x squared plus 4x all over x plus 4 by x minus 3. And then we'll just hit any like terms. So f plus g of x, x cubed minus 2x squared plus 4x over x plus 4 by x minus 3. And let's see, we can do a little bit of factoring, but nothing that would cancel either of those guys. So here, our domain, we don't have any radicals to worry about, but we do have potential division by 0. So negative 4 is out, positive 3 also out. So either negative infinity up to not including negative 4, union negative 4, positive 3, union 3, infinity. Or if you wanted in set builder notation, set of all x such that x is in the set of reals, x is not equal to negative 4, x is not equal to positive 3. All right, so that's our sum. Our difference would look pretty similar. So f minus g of x. So x squared over x plus 4 minus x over x minus 3. By the way, they could also have asked us for g minus f of x, just like in the set of real numbers. In functions, subtraction is not a commutative operation. So the order does matter, so watch out for that. This one they did want f first. So just like the last one, build up your LCD. So we multiply top and bottom by the same thing. We multiply by something worth 1. Change the look, but not the value. So we have x cubed minus 3x squared. Careful here, you're distributing not just x, but minus x. So minus x squared minus 4x all over that same LCD from last time. So f minus g of x, x cubed minus 4x squared minus 4x. Again, I can do a little bit of factoring, but I wouldn't get either of these guys, so it won't reduce. So the domain is the same as the previous f times g of x, x squared over x plus 4 by x over x minus 3. That one's a little faster, x cubed over x plus 4 by x minus 3. Domain is the same again. F over g of x, however, x squared over x plus 4 over x minus 3. So clearly the negative 4 and the positive 3 are still out. But remember, division turns into multiplication by a reciprocal. So this means 0 is also going to be kicked out of our domain. So we have a little bit of simplifying there. X squared over x is just x. So x by x minus 3 over x plus 4 is as far as we can take that one. So then our domain, we still can't use negative 4. We union that up with negative 4 to 0 this time because of this right here. Union that up with 0 to positive 3. Union that up with 3 to infinity, so we have more restrictions. If you like, you can just do the set builder instead. Set of all x such that x is in the set of reals. X is not equal to negative 4. X is not equal to 0. X is not equal to 3. Okay, so that should give you enough practice with 2.1. So 2.1, I would try 1 through 18 all, 19 to 89 odd, 101 and 111, or the equivalent ones on the MyMathLab. If you have any questions, please get in touch with me. Otherwise, I will see you next time. Stay safe out there.